At its very core, drug science must remain independent. This means we don't accept sponsorships. It's with the support of the drug science community we're able to do this and make the podcast in the first place. If you're able to become a drug science community member and support the show, you too will be supporting the dissemination of evidence-based drug policies. Without you, none of this would be possible. For anybody interested, there's a link in the show notes. Thank you. Hello and welcome to the Drug Science Podcast with me, David Nutt. Here we're bringing together experts and activists for a rational, honest and informed conversation about drugs. Hello everyone, I'm David Nutt and here's another Drug Science Podcast. And today I have with me someone that I know rather well, Robin Carhart-Harris. We've worked together for, I think, at least 15 years. And of course, Robin's known to many of you for his pioneering studies on how psychedelics work and how they can be used to develop innovative new treatments for mental disorders. So welcome, Robin.
Thanks, David. Great to be with you.
And good to be seeing you in these strange times. So when I do these interviews, I like people to get a sense of where people came from. And I think you started off doing psychology, is that right?
Yeah. So I was doing a master's in psychoanalysis of all things, and yet you still saw me when I reached out with a request to do a PhD on LSD brain imaging, but you still saw me. So yeah, thank you.
No, and why did you do psychoanalysis, and why did you get interested in psychedelics? Can you share that with us?
Yes, absolutely. I was, I guess, drawn to just wanting, a young man wanting to understand myself, I suppose, and I felt that mainstream psychology wasn't giving me enough. It was quite superficial, and cognitive psychology is interesting, but it doesn't go that deep. And I was finding in depth psychology, Sigmund Freud and later Carl Jung, I was finding that depth, and I was really enjoying it. So I really enjoyed that master's. And it was during that master's that I discovered the literature on psychedelics, and that opened everything up for me in my mind.
So you, in your mind, put together the possibility of one facilitating the other, presumably psychedelics making sense of psychoanalysis. Was that the thought?
Yeah, it's a funny thing that happens when you find someone else's idea and you think it's your own. I saw it there in Stan Grof's work. He was saying LSD offers like laboratory evidence for the existence of the unconscious mind. And I just devoured that book. And I remember writing to him saying, I've got this idea that, ridiculous looking back, sort of that psychedelics are these research tools to allow us to understand what the unconscious mind is on a biological level. And silly thing to say, because the guy was already saying that in a sense in his book. But that was the initial inspiration.
Did he write back? Did Stan write back?
No, he didn't. I mean, years down the line, he has, and I've had a really nice exchange with him. Met him once in person.
So you had this idea, and then you've written about this, I think, haven't you? You've written about the neuroscience of psychoanalysis from a brain science perspective.
Yeah. So the first paper I wrote is called Waves of the Unconscious. And I remember when I wrote that paper during my PhD with you in Bristol, and I showed you that paper, and you said something along the lines of, yes, all papers count, Robin. There are grades of quality, and all papers are on a continuum of some degree of quality. Otherwise saying, whatever, I think, to be honest. But I could look back on that paper and be a bit embarrassed about it, but it was the first thing I ever wrote, and it was essentially saying psychedelics are a very powerful research tool to understand the brain basis of the unconscious.
Yeah, and then you came to try to do a PhD with us, didn't you? And I think you were put on to us by Amanda Fielding, who I've also recently interviewed for this podcast. So how did you find her and come to us?
I found you in parallel. So, yes, there was a common link, and it's terrible because I always forget her name, but I have thanked her, but years have passed now, but she put me on to both of you, and I wrote in parallel, and I I sort of intimated to you that there might be some support from the Beckley Foundation, and then intimated to Amanda that maybe David would be interested. So I've played a little game there, but it sort of worked out, and I got to meet you both. And yes, and we've been quite a productive team, haven't we, over the years?
No, indeed, a phenomenal little triad. But you didn't start working on psychedelics, did you? Most people don't know this, but I think your original PhD study was on MDMA, and it was actually, I think, quite an important one. Can you share that with us?
Yes, happily. Yeah, you were right, David. I had to cut my teeth in basic psychopharmacology before taking on something as wildly ambitious as the first ever brain imaging research with LSD, and we did psilocybin first, of course. But so the PhD was understanding the serotonin system. It was focused on the serotonin system, and with Sue Wilson, who was a great supervisor for my PhD, sleep expert and serotonin expert. We use tryptophan depletion, a dietary manipulation that starves you of a essential amino acid that's the precursor of, you need it, serotonin in the brain. So we starved people of that precursor of serotonin, so depleted their serotonin levels, and then recorded their sleep. And it was a way to stress the serotonin system in MDMA users and match controls to see whether MDMA users had damaged serotonin systems. That was my PhD, yeah.
And a lot of people don't know, the fact that you found that they didn't.
That's right. They had the same quality sleep, which might surprise some people. So it wasn't looking at the acute effects of MDMA on sleep. It was looking at whether, sleep generally had been disturbed. Sleep as an index of serotonin system was abnormal potentially because of excessive MDMA use. And we found it was a negative finding. We saw comparable sleep in the two conditions, MDMA users and matched controls. However, tryptophan depletion worked beautifully. It shortened the latency to REM sleep, so you go into your dream sleep more quickly. I think there was a more quantity as well, a longer duration of REM sleep.
And if you can remember when we first, I think we did the study because McCann and others at Johns Hopkins had done a study saying that MDMA users had disrupted sleep, and this was proof of MDMA brain damage, wasn't it? And we sent it off to the same journal that had published that original paper. Do you remember that?
Vaguely, to be honest, but I remember the climate at the time, that was so weighted against MDMA. Was all of the papers were about, whether it was behavioral indices of serotonin damage or actual claims of serotonin damage. So we were kind of going against the grain and reporting a negative finding.
Well, I remember it vividly because I remember the editor writing back saying, we're not going to referee this, David, because there's no referee in America that would agree with you because you're contradicting the standard polemic on MDMA, which I thought was actually both honest, unusually so, but also it saved us a lot of time. We could have wasted years trying to get it published against a backdrop of hostility to having evidence about MDMA out there in the public domain. So, yeah, it was. I think you should celebrate that study because I think it's the most sophisticated and best designed study that really tests the question, does MDMA use affect serotonin function when it's under stress? And it didn't seem to.
Yeah.
But that's not the only experiment you've done with MDMA. Let's talk about the Channel 4 program first, and then we'll get on to psychedelics.
Yeah.
Tell people about the Drugs Live.
Yeah, wow, what an experience. Well, yeah, I mean, you very much brought that to me, this opportunity to be part of this project funded by Channel 4 to do some brain imaging research with MDMA, the first thorough fMRI assessment of the acute brain effects of MDMA. And we had that funding from Channel 4 because they wanted to make a documentary on it, a live documentary, a live show on, the big idea that they had was celebs taking ecstasy. That was the hook. And it didn't quite sort of transpire that way. There was one, member of the public who was filmed live under the influence of MDMA in the studio in Chelsea, I remember, next to the football ground. Yeah. But it was an incredible experience. And the thing that I take most from that wild life experience, which was fun and stressful at the same time, was the science that we got to do. I mean, it was worth it. Worth, all the complications that come with working with media in such a close way as we did there. And yet we did get to do some quality science. And I'm quite proud of our, I think, biological psychiatry paper that we got from that research. And I think it remains the kind of, sort of key publication in terms of the acute brain effects of MDMA.
No, I think undoubtedly, and it's actually obviously spawned quite a lot of interest in the utility of MDMA. It kind of was the underpinning. It gave a scientific underpinning to the work in PTSD and more recently Ben Sesso's work in alcoholism. So yeah, absolute landmark paper. But probably overshadowed by your work on psilocybin and LSD then.
Well, yes, labour of love. Monomania in a sense. Brain imaging research with the classic psychedelics, and thank you for the opportunity to realise that dream.
Well, tell people about it. Tell people what you did, because not everyone they'll know you've done a lot, but they won't probably know exactly what you've done. And maybe start with psilocybin. Why did you start with psilocybin?
Psilocybin was less controversial, and Franz Vollenweider in Zurich had done some PET imaging with psilocybin, so we could take that to an ethics committee and say, look, somebody else has done this before and no one died, no one went mad, and we think we can do this. And when we found over the years, haven't we, that when you lay out the evidence, it's quite compelling actually, that the safety profile supports us being able to do this research. And then over time we discovered, the therapeutic potential, and the narrative has shifted quite dramatically. But back then, yes, the quest was to do some brain imaging work with classic psychedelics with that simple big question, how do psychedelics work in the brain? Why do you trip? And so we used various different brain imaging modalities, beginning with fMRI and two different flavors of fMRI, one looking at blood flow, arterial spin labeling, and then one looking at functional connectivity, the spontaneous fluctuating activity in the brain with the bold signal of fMRI. And that was the first fMRI research certainly with psilocybin, if not the first with a classic psychedelic, certainly the first resting state. So asking that big question, what changes in your brain when you're tripping on a psychedelic, so to speak.
Just explain to the listeners a little bit about when you made that comment about resting state. They won't necessarily understand what you mean. So can you expand that a bit?
So for a long time, the dominant paradigm with functional brain imaging, and in particular fMRI, functional magnetic resonance imaging, the dominant approach was to throw a task at someone, get them to do something in the scanner, and then you would see a little increase or decrease in activation in different brain regions. You could imagine a simple task as eyes closed versus eyes open. You get activation, you get an increase in the bold signal in the visual cortex. And so that was the way that you do fMRI. But then things started to change in around about the early 2000s, where people started to look at spontaneous brain activity. And when you're asking a big, broad question like, how does a drug that profoundly alters your conscious experience work in the brain, that's what you want to look at. You're not interested in how it modulates how the brain responds to some specific behavioral paradigm. You want to know a more fundamental question: what does it do to ongoing brain activity? So I use these terms interchangeably: ongoing brain activity, spontaneous brain activity, resting state brain activity. It's all the same thing. Resting state's a little bit of some have argued a misleading term, because we're never really resting. You close your eyes as you do during a resting state scan and just lie in the scanner, passively lie in the scanner. But your brain and your mind's going 10 to the dozen. You're thinking about this and that and the other, as we do. And so can you really call that resting state? But we do. Yeah.
And so you did it. You did the experiment, and I think we're slightly surprised by the results, yes?
We were, weren't we? And we went back and forth with Richard Wise at Cardiff. Have we got this right? Have we done these analyses right? And then we analysed them a different way. And then we looked at the bold data. and they converged. And the finding was a decrease in blood flow throughout the brain, and then a decrease in bold signal as well, quite widespread across the brain again. And so that was surprising because it was inconsistent with some of Franz Vollenweider's work, where he'd reported increases in glucose metabolism in the brain with psychedelics. And, that's been I think over time we've started to scrutinize brain function in a more sophisticated way, such that those old measures are somewhat less useful. But that was an early sort of inconsistency with the little bit of data that already existed. And it was a bit of a head scratcher for a while. Why are we seeing these drops in activity with a drug that, so profoundly alters conscious experience? And I remember the narrative that we went with was that, the regions that we're seeing implicated here are regions that constrain brain function. So it's like releasing an inhibitory hold on brain function. And I think that narrative, that general narrative, still holds up today.
But of course, that's been developed by many of your mathematicians you've collaborated with, who've done some very elegant analyses on connectivity as a result of those changes. Can you, in simple words, explain to the world what that's discovered?
Yeah, I'll try. I suppose those early measures were they were looking at quantity of brain activity, like quantity of blood flow. Is it less or more? And it's a bit of a crude, blunt tool way of looking at brain function, treating it almost like a thermostat. Is it hot or cold? And is the blobbage red or blue? But over time we've started to probe the brain in a more meaningful way, I think, and instead look at the quality of brain activity. And this is where the shift came in my mind, that what we're seeing is that these psychedelics are altering the quality of brain activity. What do I mean by that? The activity, the spontaneous ongoing brain activity, becomes less predictable. It becomes disordered, or entropic is the fancy term, but it's also the formal term. It's the right term. Could I say that in a simpler way? It's like brain activity becomes kind of scrambled.
Mm-hmm, mm-hmm. So the normal ongoing activity is disrupted. And why is that important for our understanding of things like consciousness then?
So it transpires that there's really quite a reliable relationship between the entropy or the predictableness of brain activity and one's level of consciousness. So when we knock ourselves out, or someone knocks us out with an anesthetic, or actually with a blunt instrument, if we're knocked unconscious, if we're unconscious, brain activity becomes very predictable, like slow rolling waves. There's no real informational richness in that brain activity. It just rolls up and down. Same when we fall into deep sleep. So there's that. And then in normal waking consciousness, brain activity is comparably much richer. It's much more entropic. And what we discovered with psychedelics is that it jumps up a level still. It becomes even more entropic than the highly entropic quality, highly information-rich quality of brain activity during normal waking consciousness.
Oh, so you think the psychedelic state is a higher level of consciousness?
I'm not sure I'd want to drive that narrative too much, but it's not without some foundation that the activity is informationally richer.
Yes,
under a psychedelic.
And I think we'll come on later to talk about the depression work, but I guess the fact that under psychedelics people can remember things that they've forgotten and understand things that they never understood before suggests that at some level there's a higher level of, a greater level of insight perhaps than you have in normal consciousness.
Yeah, maybe expanded is okay. I do feel quite comfortable with saying it's an expanded repertoire of information processing under a psychedelic. And
so not content to just use the fMRI technology, you then went off to Cardiff, I believe, and did something called MEG. Can you explain why and what you found?
Yeah, that's right. With Suresh in Cardiff, Cardiff had been a great early collaborator there. We did our fMRI, most of our fMRI in Cardiff as well. And MEG, magnetoencephalography, closely related to EEG, the better known EEG, the kind of, swimming caps that people have seen with the different sensors around the skull, picking up electrical activity from the cortex. So MEG is a great tool. It's like super EEG, has a bit better spatial resolution than EEG. It's got like, a couple of hundred plus sensors, whereas EEG typically it's like 30 odd sensors. And the great thing about MEG and EEG is you're recording neural activity. With fMRI, you're sort of like picking up this signal through changes in blood oxygenation, and you're never quite sure whether it's being confounded by, physiological changes. Whereas with the MEG and EEG, you know where you are. This is neural activity. And we've found changes in brain activity in similar regions that we'd seen in the fMRI. And we saw these drops in what we call power, which is the amplitude of the different rhythms in the brain. They were becoming shallower in their oscillating activity, and that sort of collapse of the brain's normal rhythmicity was correlating with the intensity of the subjective experience. And it transpires actually that I was talking about that entropic effect, that this is related. You can imagine the big rolling waves, like the big rhythms. Under the psychedelic, we're seeing these much shallower kind of, ripples on the surface.
Hi, it's David Nutt here again. I want to take a moment to thank all of the drug science community members. In a world of paid sponsorships, political and commercial interference, drug science is and always will be independent. If you value the show as an educational resource and want to help keep us going, you can do so at drugscience.org.uk. Without our community, the dissemination of unbiased information would not be possible. By becoming a drug science community member, you help to create a world where drug control is rational and evidence-based, where drug use is better informed and drug users are understood, where drugs are used to heal, not harm. Furthermore, by becoming a premium community member, you will receive a signed copy of my autobiography, access to exclusive events. At the end of the season, we will be hosting an exclusive Q&A podcast episode with all of our premium community members, where you can ask me anything. You can find out how to do this in the show notes. So now, thank you, and back to the show. So one thing that came out of those two studies together was the discovery of something I'd not heard of before, of the default mode network being particularly perturbed by psychedelics. Can you explain to people what the default mode network is and how that perturbation is relevant to the effects?
Yeah. So I suppose we started to do our brain imaging work, more or less a decade after the default mode network was discovered. So it was this very hot topic in human neuroscience. And I suppose what was most exciting about it was that it seemed, kind of special, a special network in the brain, more metabolically hungry than elsewhere in the brain, consuming more of already the brain's, massive energy consumption, but disproportionately so in this default mode network. More blood flow, more densely interconnected network. Now we know other properties that hierarchically the DMN sort of sits at the top of the cortex as the most high level network associated with human specific aptitudes, imagination, the ability to have self-reflection and such like. And so when we looked in our brain imaging data under psychedelics and saw this network implicated, it was one of those moments where you smile and you think, and I suppose the initial thought was, is this ego dissolution? Initially, we were seeing drops in blood flow, drops in bold signal, and then over time, it became more of like a scrambling effect. And actually, you could call it, although it's transient, you could call it a disintegration of the default mode network. And lo and behold, for years, people have used this term ego disintegration. So it was kind of a neat, natural mapping there. And then we saw correlations with, decreased connectivity within this default mode network and ratings of ego disintegration. So I think still, now, I guess a decade on from our PNAS paper first reporting this DMN disintegration, that feels still like a, somewhat reliable thing to say. It's become more nuanced, I suppose, but, disintegration of the DMN and its relationship to experiences like ego disintegration under psychedelics is a pretty...
So the default mode network is where your ego is encoded, effectively.
Yeah, but I would say it's more in the dynamics of the default mode network, because, no brain region, and certainly, also no brain network is an island entire to itself. Yeah, all of these systems are interconnected. And so it's more about what the DMN does, that it's functioning, its dynamics change. And what's the simplest thing to say about that, to unpack it? You could say, well, the nodes that make up the network become less strongly interconnected. So within the network itself, it disintegrates or decreases in what we call functional connectivity, the strength of the communication between the different nodes. But then when we look outside of the network, we see it becoming more communicative with other systems. And that's the other general rule that's, I would say, we've kind of, discovered that, is this increase in between network communication, or I could try and say it a bit simpler, an increase in global brain interconnectivity under psychedelics.
Maybe people won't fully understand the concept of that there being different networks in the brain. Could you, just briefly make sense of that for them?
Yeah, sure. So I guess over the last 20 years or so, cognitive neuroscience, human neuroscience have identified some what we call canonical brain networks, some like standard, it's like the alphabet of the brain. These are the basic sort of network building blocks. So we have a network for vision. I'm saying it very simply here, but we've got a network for vision, a network for hearing, a network for moving our bodies. And then we've got these higher level networks that do things like attention. They're involved in encoding and processing the outside world and our ability to attend and scrutinize in an analytical way the outside world. And then other networks like the default mode network seem to be more related to processing, you could say, our internal world. So functions like imagination, mental imagery, mental construction, imagining the future, reflecting on our past, that sort of DMN territory, default mode network. So these are the sort of, simple building blocks of the brain, these networks.
And why would psilocybin disrupt it?
Well, so we can go right down to the molecular level here and talk about the serotonin 2A receptor, which is the most important receptor or, button in the brain that if you push, this is that you need to push this button to make psychedelics work. And these 2A receptors, these serotonin 2A receptors, they're serotonin receptors, and they're highly expressed in particularly these high level brain networks like the default mode network. And it transpires that these are also the aspects of the brain that have so massively expanded in our species. And even more tantalizing, we now have evidence that's barely a year old that the serotonin 2A receptor that psychedelics work on is closely implicated in cortical expansion, or the evolution of the brain, the evolution of the human brain.
So the 2A receptor has a special function, you think, in relation to being human?
Yeah. We're not the first to think that. Famously, Terence McKenna had this stoned ape hypothesis that, ancient sort of early humans or pre-humans ingested psychedelic mushrooms, and that was the catalyst of brain expansion. I don't think this recent evidence is evidence for the stoned ape hypothesis, but he wasn't far off, is what it's looking like now. It's just he was a bit too psychedelic centric. I think it's more kind of simpler and more plausible to think it was serotonin that did it through its 2A receptor.
Right. And then we went on to make sure it wasn't just some peculiarity of the magic mushroom, because you then went and studied LSD and DMT, and just tell the listeners a bit about those results, please.
Yeah, so with the LSD, we used two modalities in one go. People went into the MRI scanner and they had a bit of a break, did some interviews, did some ratings, and went into the MEG scanner. So it was quite a tall ask, really, to have people do that, quite sort of exhausting for them. And there, it was a neat design because we could compare the two within the same people and within the same session. And in a sense, I suppose the LSD findings were just a a better quality version of what we'd done with psilocybin. And we published all of that together. And because of some uncertainty that remained about seeing brain activity through this complex physiological measure that you get with fMRI, when we could twin it with MEG in the same study, it became much more compelling that, yes, these are, changes in neural activity in the brain. They interrelate, they correlate with each other, they correlate with the subjective experience. So that was our 2016 PNAS paper. Probably a kind of, I think it's fair to say, without sort of boasting too much, that was a seminal paper in the neuroscience, the human neuroscience of psychedelics.
And DMT, you think that's the same as well?
Yeah, whether or not there's anything that's extra with DMT is a work in progress, I would say. So we're seeing a lot that's consistent. We see the collapse in the alpha rhythm. We see the networks disintegrate and then increase global interconnectedness. But in the EEG, we're seeing some signs of the emergence of some other rhythms. So as the alpha kind of gatekeeper collapses, and that we think that has an inhibitory hold on the brain, then it may be that allows for the emergence of some other interesting rhythms, some slower rhythms. If their source is deep, they might even be related to, you could call the older brain, the limbic brain, the mammalian brain, an aspect of our brains that engages during rapid eye movement sleep. Maybe it relates to some of the dreamlike visionary qualities of a DMT trip. It's just difficult to say, but there's a few different lines of evidence that are pointing in this direction of emergent rhythms with DMT.
Okay, so let's just move on now to, having sorted out consciousness and the role of 2A receptors. You then went on to study depression. Well, why did you do that?
Well, it was a team effort, wasn't it? I mean, it was I think, a mutual knowing. I think I can remember you saying, let's do it. And I sort of looked at you and said, really? You're like, yeah, let's do it. Let's write to the MRC and say we'll do a depression trial with psilocybin. And that was born out of, I guess, listening to our participants who were saying, I feel really good. Like, I feel like a weight's been lifted from my shoulders. And I'd say, well, we injected you with psilocybin in a brain scanner and you're telling us that you feel really good. Something's going on here. And then we looked in the brains, of course, and we saw some changes particularly in brain blood flow and bowl signal in a certain region of the brain, the medial, ventromedial, prefrontal cortex, close to something called the subgenual cingulate cortex, that at the time was the hotspot in depression research. So much so that Helen Mayberg pioneered this deep brain stimulation. This Canadian, I think, American neurologist pioneered this deep brain stimulation for depression, for very severe treatment-resistant depression, targeting this subgenual cingulate cortex to shut it off, essentially, to inhibit its activity with electrical stimulation. We were so inspired by that, and then seeing the blobs in the brain under psychedelics in the right regions, the consistent regions, we thought, well, psychedelics for depression. Let's write this up and put it to the test. And the MRC, took the bait and got some great reviews there across the board. I think top marks, and got it over the line. And long story short, we did that first trial in treatment-resistant depression. We had to compromise on a lot of things. We wanted to go with a really nice double-blind randomized control trial design, but circumstances prohibited us from doing that. It was really hard to get the ethics. It took us 3 years to get the ethics and the drug. And by that time, we were running out of money, so we could only get a single blind study done in 20 people, but we got it done, and what a difference it's made, because we saw those remarkable findings, the rapid drops in very severe depressions, and then they appeared to be quite enduring in a good proportion of the volunteers. Yeah.
So these were patients who had what we call treatment resistance, I think.
Yes, that's right. They had treatment resistant depression. Some of them had taken 11 different medications in their current depressive episode and said that they've had their depression for, I think it was an average of 17 or 18 years. And so, very difficult to shift depression. And we came in with psilocybin, and what do we have? Did we have about half in remission at the end of the trial period? It's something like that, wasn't it? Yeah.
After just a single trip. Yeah, that's the most remarkable thing,
Yeah.
a single trip.
Single full dose. Yeah, we had 2 doses. One was a kind of starter dose, a sort of feeler dose, and then the big dose. So, yeah.
And I think also the brain imaging suggested perhaps a slightly different mode of action to conventional antidepressants, didn't it?
Yes. We saw these curious, anomalous increases in amygdala, this emotion center in the brain, wrongly, sometimes called the fear center. It's not just fear, it's any salient emotion. But anyway, this emotion center is sensitive to emotional stimuli. So we throw emotional faces at people on a screen in the scanner and see the amygdala activate. And what we found with psilocybin when we scanned people a day after their big dose was that this emotion center was more responsive. And that was anomalous because SSRIs, standard conventional antidepressants, do the opposite. They sort of blunt or mollify the responsiveness of the amygdala to emotional stimuli. And so, that was one of those cases where we've got an interesting finding that sort of bucks the trend and gets us thinking about why this treatment's different. Now, it transpires in our more recent work that if you look further out, like a month later, you see something a bit more like you see with SSRIs. You see a reduction in brain responsiveness, particularly to negative emotional stimuli with the psilocybin. And other teams have shown that now as well. Hopkins have shown that. So what we think we picked up is this, emotional rawness, this like thin-skinned quality that people have very soon after a psychedelic experience, where we think the therapeutic component of psychedelic therapy is particularly important.
Yeah, and you came up with the idea that there are effectively 2 separate ways you can use serotonin to treat depression. One through drugs like the SSRIs and one through drugs like psilocybin, but they're very different parts of the brain and different receptors. Could you just give the listeners a little précis of that theory?
Yeah, so that was our Tale of Two Receptors paper, and that was born out of, I guess, a realization that SSRIs work on a different component of the serotonin system to the component that psychedelics work on. And we kind of simplified it for the sake of, comprehension, really, that SSRIs, generally speaking, have quite a dominant effect on receptors, serotonin receptors in stress circuitry, and those are inhibitory receptors. And so their general effect is to sort of blunt responsiveness of stress circuitry to, emotional stimuli or stressors. And that's kind of how SSRIs work. I think it's fair to say that's what we say in the paper, that they help take the edge off, help you get by, through controlling stress and reactivity. But with psychedelics, it's kind of the opposite. It's like an emotional release rather than an emotional blunting. And people are going to see that in our more recent trial reports, recently published, coming out in New England Journal of Medicine.
Okay, so you have this theory then that you've got the subcortical, the limbic system being dampened down by this anti-stress effect of SSRIs working on the serotonin 1A receptor. You've got the opening up of the mind and through the 2A receptor, and allowing people to think differently about their depressions and perhaps overcome them through some kind of insight. And then you went out to test those theories in a head-to-head. So tell people about this head-to-head study you've done.
Sure, yeah. So I guess that was a tantalizing prospect, came from, yes, that sort of basic pharmacology, but also what people were saying from our TRD trial, where all of them had a history of being treated with conventional antidepressants. They had to have had that to get into the trial. And yes, there's a bias here because they didn't respond. Otherwise, they wouldn't be treatment resistant and depressed. So they had a big downer about SSRIs and said, they're no good. But it was also a source of inspiration to think, well, given that they did respond to psilocybin, what would happen if we went and put these treatments into a head-to-head? And yeah, that's what we've done now in a sample of close to 60 people, 2-arm trial, fully randomized and double blind. And people either go into a condition where they get 2 big doses of psilocybin, 25 milligrams, 3 weeks apart. And then alongside that are taking placebo capsules every day. Or they go into the other arm that we call for simplicity the escitalopram arm, where they do get a little bit of psilocybin. They get 2 1 milligram dosing sessions, but you compare that with 25, 1 milligram we assume to have negligible activity. It's a placebo dose of psilocybin. But we do that so we could standardize expectations and tell all our patients that they will receive some psilocybin. Probably helps with recruitment as well.
Indeed.
And then if you go to the escitalopram group, you're taking escitalopram every day for 6 weeks, 10 milligrams for the first 3 weeks, 20, which is the recommended maximal dosage of escitalopram.
Oh, that's a good dose. Good dose. Mm.
Yeah. So we gave it I think it's fair to say, a decent crack of the whip, and then set our primary endpoint. So where we put the sort of finish line, we put that at 6 weeks. So 3 weeks after your second psilocybin dosing session, or at the end of your 6-week course of escitalopram, and then we make our comparison.
And what did you find?
And drum roll.
That's right, drum roll.
Yeah. So in clinical trials, you have to set your flag somewhere. You have to identify your target, call it the primary outcome, and say this is the key comparator. Now, on that key comparator, there was no statistically significant difference between the conditions. Psilocybin was a few points better in terms of dropping depression scores, but not quite enough to give you 95% confidence that this is a true, reliable effect. However, if you look at other outcomes like remission rates, they were twice as high with psilocybin than escitalopram at the end of the trial. Response rates, 70% with psilocybin versus 50% with escitalopram. I think 50% more or less what is kind of standard for antidepressants, conventional antidepressants. And then we look at other things, what we call the secondary outcome measures, things like general functioning, work and social functioning, all sorts of things, anxiety, well-being, almost across the board. I think across the board, they all separated in favor of psilocybin. So while psilocybin missed on the primary outcome, it felt like kind of sod's law. It was almost the only measure that psilocybin didn't significantly separate from the escitalopram.
And it did it faster.
Did it faster, yeah. Yeah, and it separated there at 1 week.
So you vindicated, and I suppose we're now waiting on can you comment on the brain imaging study? Have we confirmed the theory through the imaging, do you think?
Well, we've moved it along. We've moved along the theory, and it's quite satisfying when that happens. So there's more to the story now, and it may be that what we picked up in the past is just part of the process, the therapeutic process, the emotional rawness that you see the next day, and maybe also the kind of spacious self-reflection that you often see after a big psychedelic experience. We saw this expansion in the spatial extent of the default mode network one day after psilocybin in our treatment-resistant depression trial. But now we're seeing something a little different. We're seeing the brain's response to emotional stimuli being less responsive to negative stimuli with the psilocybin, and with the escitalopram, this is now at the end of the trial, so a few weeks after the intervention, less responsive to specifically negative stimuli with psilocybin, but with escitalopram, it was less responsive across the board to emotional stimuli.
So it's a blunting with the SSRI and a kind of resetting in a more positive direction with the psilocybin.
Yeah, because there was no blunting in the brain's response to positive stimuli with psilocybin. So yes, you could I think you can frame it that way. Yeah, generalized blunting of emotional responsiveness.
And of course, your work in depression has spawned its enormous interest in companies in developing psychedelics. Now, there seems to be a new one every week. So you must take a bit of pride in the fact that you've kickstarted a whole new branch of psychiatry.
Yeah, I guess the most satisfying thing is when you know that this will move the quality of treatments along, I think, and broaden the toolkit of clinicians. That's really satisfying. And, it's nice to reflect that there's hope now for people when they're suffering from depression and think it's a coin flip whether they're going to respond to the best available treatment. We can do better than a coin flip with psilocybin therapy.
Well, that's extremely encouraging, Robin, and I congratulate you again on the amazing work you've done over the last 15 years. And it's good to see someone coming into science with a question and a vision and actually achieving to a large extent what you set out to do. So well done, and I'll wish you well in the rest of your career, and recommend that everyone looks out for this paper, which is published in the New England Journal of Medicine. Congratulations again, and thank you for sharing your insights with us on this podcast. Thank you.
Well, my pleasure, Dave. If there's time, I just want to say thank you for giving me the opportunity.